Welcome to Lesson 10a, Diffusion of a Vortex Sheet. In this lesson, we'll look at two-dimensional vortex sheet flow, and we'll develop a similarity equation for the flow, which we'll be able to solve. Then we'll discuss the diffusion of vorticity and momentum in this flow, and plot similarity profiles. As a quick review of similarity solutions, in a previous lesson we solved Stokes' first problem, an impulsively started wall. The second similarity problem will be diffusion of a vortex sheet. Here's the setup. We have an infinite flow field in all directions. Above the x-axis, the flow is at capital U to the right, and below the x-axis, it's in the opposite direction. Gravity acts in the minus y direction. This flow is two-dimensional, meaning that del z of anything is 0, and there's no w component of velocity. We'll let p equal p naught equal constant along the x-axis, where y equals 0. This is our gravity vector. There's no imposed pressure gradient. In other words, we're not pushing this flow in any direction. This flow has an initial discontinuity at time t equals 0 with this velocity field for u, but at t equals 0 we suddenly turn on viscosity, which remains on for all time greater than 0. Finally, nothing is special about any particular x location, so del of anything del x is also 0. With these assumptions and approximations, we can solve the problem. First, a comment. This is an inviscid flow at time t equals 0. If we never turned on viscosity, this flow would just stay like this forever. But at t equals 0, imagine turning on viscosity. So for time greater than 0, this is an unsteady laminar flow. If you think about it, it's very similar to Stokes' first problem, except instead of a wall here at the x-axis, we have fluid moving in the opposite direction. As we'll see, we need three boundary conditions for u as a function of y and time. We already have one from our problem setup. At t equals 0, u equal capital U for all y greater than 0, and u equal negative u for all y less than 0. I'll ask the students, what two other boundary conditions must we impose?
Well, since the flow is infinite, lowercase u must approach uppercase U as y approaches infinity.
Right, Boris. What about the second one?
Dude, that one's easy. As y goes to negative infinity, little u has to approach negative big U.
Right, Joe. And these two boundary conditions apply for all time. I'll write them out here. At y going to infinity, u goes to capital U for all time. And as y goes to negative infinity, u goes to negative capital U for all time. Now let's solve this problem. It turns out that the math is nearly identical to that of Stokes' first problem. Namely, our differential equations become, for continuity, v equals 0 everywhere, same as Stokes' first problem. Y momentum reduces to p equal p naught minus rho gy, which is also the same as Stokes' first problem. Namely, we simply have hydrostatic pressure. And when you go through the x momentum equation, only two terms remain. Del u del t equal nu, del squared u del y squared. These are all identical to Stokes' first problem. But we don't have the same solution because the boundary conditions are not the same. We're solving this same equation, the simple 1D diffusion equation, for both of these problems, but with different boundary conditions. Again, just like with Stokes' first problem, we expect a similarity solution. Since there's no length scale in this problem, remember the ant and giant argument, we have the same situation here. In fact, let's use the same similarity variables that we used in Stokes' first problem, which you may recall. We let eta equal y over delta of t, where delta is some measure of the thickness of the diffusion layer, and f of eta is u over capital U. The same algebra again as in the previous problem gives us delta, the same delta as before, where c is an arbitrary constant. And after a bit more algebra, we get an ordinary differential equation, which is identical to that of Stokes' first problem. So similarity has been achieved for the equations. Our x momentum equation was a partial differential equation of second order in u, and now we have an ordinary differential equation, still of second order, but we've combined y and time into one similarity variable, eta. and f, of course, is a function of eta only. This is an ordinary differential equation. So we've reduced the number of independent variables by 1, which is always our goal in similarity solutions. But what about the boundary conditions? We had 3 boundary conditions, and since we need only 2 here, the boundary conditions must combine to give us only 2 that are not inconsistent. Let's check this out. We had at t equals 0, u equal capital U for y greater than 0, and u equal negative capital U for y less than 0. But at t equals 0, the thickness delta must be 0, and since eta is y over delta, eta must go to infinity at t equals 0. So this first boundary condition becomes f of infinity equal 1 for this portion, and for this portion, f of negative infinity is negative 1. Well, these are the 2 boundary conditions that we need, but what about our other 2 original boundary conditions in physical variables? Namely, at y going to infinity, u goes to capital U, which gives us f of infinity equal 1, and at y approaching negative infinity, u approaches negative capital U, which gives us f of negative infinity is minus 1. These are the same, and we've reduced our 3 boundary conditions in physical variables to only 2 boundary conditions in similarity variables, which is appropriate for our second-order ODE. Thus, we can finally say similarity has been achieved. Now, what about the solution to this equation with these boundary conditions? Well, it turns out, without doing all the algebra, that we end up with an error function just as we did with the previous problem. Our solution is f of eta is the error function of square root of c over 2 eta in similarity variables. Remember that c is arbitrary, so if we pick any constant c or just let it stay as c and do a little bit of algebra, we can convert this to physical variables and c will drop out. Here's our final equation in physical variables. What does it look like? Well, we can plot x and u velocity as a function of y with negative capital U and positive capital U on our u-axis. At t equals 0, the velocity profile has a singularity, but at some finite time, the profile will look something like that, and at some later time, something like that, where time is increasing as vorticity and momentum diffuse into the upper and lower flow fields. But because this is a similarity solution, this equation holds for all time and all y. So alternatively, let's plot u over capital U as a function of y over 2 square root of nu t, this variable, which is non-dimensional, by the way. Both of these are non-dimensional. Instead of going from negative u to u, we go from negative 1 to 1, and we have one curve, one profile, that works for any of these physical profiles. This is our similarity profile. Thank you for watching this video. Please subscribe to my YouTube channel for more videos.
1, 2, 3. That's all there is to it.